Hi guys, even more problems from AdCoder regular contest coming up your way today. So I wanted to start with a very beautiful problem, or at least what I consider to be quite beautiful. Uh, it's a tricolor pyramid, and the description is quite simple. So what we have in this problem is like a row of let's say letters. It can be blue, white, or red. And then there is a rule of how we can combine two letters to get the next row, and then the next row, and so on. And what we want to find is what will be the topmost block after this process. And the difficulty, of course, lies in this row being enormously large, so that we can't explicitly generate the triangle, or the pyramid, as they call it. So what we should do is we should come up with a way to find the color of the topmost block much faster than in quadratic time. Let's not spoil the solution to you and say what time it will be. So yeah, but judging from the constraints, both like linear and of n log n will work just fine. So yeah, and I think it's a very beautiful problem because it reminded me a lot of problems that I used to solve in high school when I was actively participating in some mathematical competitions. It looks a lot like this. You will have to know a little bit of theory to solve it, but there are two ideas to this problem. Now the first one is purely an idea, like very widely used in Olympiad math, not that widely used in competitive programming. And the second one is just like theoretical thing that you should know. You want to solve problems like this. Now, you may have noticed that I actually have not explained these rules, like how you combine the blocks. Now, you could derive them yourself from this picture. I believe it's quite obvious what happens. So I will say them out loud right now. So if we have two blocks of different colors, then we get the third color. If we have two blocks of the same color, then we get the same color. So like here, blue plus white equals red, or let's not say blue plus white equals red. Let's say blue and white equals red, and white and white equals white. And you see, in Olympiad math, it's quite common to get rid of those colors because they are kind of annoying, and change them into values. And you would normally expect the values to be modulo 3, right? But then there is a problem, because when you add blue and white, let's say white is, let's say all values are modulo 3. So white is 0, red is 1, and then blue is 2, right? When you combine white and blue, you don't actually get red, right? You get just something else. You only get white when you combine red with blue. That kind of does not work. And in general, you would expect some linear dependency between those values to show up. But unfortunately for me, I'm not very smart, so it took me quite a while to understand that I know some operations beyond addition. So after looking at this for like 20 minutes or so, I realized that if I look at 3 blocks at the same time, not just at the base 2, but let's say I look at all 3 blocks at the same time, and I notice that either we have all of them different or all the same. And I realized, so maybe I should be taking this one into the sum as well. Because what happens then is like 3 times pretty much anything is equal to 0 modulo 3, but also white plus red plus blue in any order is also equal to 0 modulo 3. So this correspondence was correct. The operation that combined them was wrong. And it took me quite a while to understand that this could happen. So as a result of this observation, we now have the following. We have a row, and we have this kind of condition, right? That's not very nice in terms of what we actually get as the top block from 2 and 0. Like you want to get 1 and you want to have a formula for this. It does not look like this, but rather that expresses the topmost block in terms of the 2 below. So currently our formula for these 3 blocks is x plus y plus z equals 0 modulo 3. And what we actually want to have is a formula for z, which is not hard to derive. So that is minus x minus y modulo 3. So yeah. And the nice thing about this minus is that it kind of flips every other row. Like values from the bottom row, they sort of get to the next row with negative sign. Then they get to the next row with a negative sign again, which ends up being positive because negative times negative is positive, of course. So yeah, these signs are not a major problem, as you can see. What is interesting is okay, so now we know that there is linear dependency. So what we're basically looking for is we are looking for some weights with which these blocks propagate via different paths into the root, into the topmost block. And well, it's not hard to see that this is just a binomial coefficient. So if you start from the top, you will see that coefficients look like this. So here there was a 1. Now we know that these guys actually get with a negative sign towards him. So these guys are actually -1, -1. And I know that this goes here, but this goes to both. So it's a 2. And then you get just your normalish Pascal triangle. So what you end up in the end, you get plus or minus binomial coefficients. Then you do your addition modulo 3, and you take the remainder and you get the correct color. However, it's a non-trivial task to find binomial coefficients of this row modulo 3. Because once again, you cannot just generate them in quadratic time. And also, normally, if you need a row of Pascal triangle, let's say modulo something huge, let's say modulo some prime number that is near 1 billion, then of course you can just you just compute factorials and inverse factorials. Inverse factorials you can compute using modular inverse. So that is not the main difficulty. But here, because the modulo is quite small, modulo is just 3, right? You cannot perform all these operations modulo 3 because inverse will not always exist. So that is a question for you that you can try to research yourself, is how to compute binomial coefficients n choose k modulo 3, or let's say modulo prime, when prime can be smaller than nk. So yeah, I encourage you to do some research. In case you don't really want to do that, I'll show the answer in a second. So what happens here is now we find a way to find the binomial coefficients to compute them, and we just compute the sum with corresponding coefficients. We take modulus 3 and we get the color on top. This kind of linear dependency between the guys was the main thing to realize. It took me quite a while that it can be with negative signs actually. So yeah, but let me show you the implementation first, and then we'll talk about this thing that it uses. So I kind of need a mapping from my colors to my remainders modulus 3, and I also need just a way to like the reverse mapping. So this is only for like mapping from characters to values and vice versa. Then I have some binomial function that will compute binomial coefficients for me. But we'll talk about it a bit later. And then we just used it to compute the sum of all values in the bottom row multiplied by binomial coefficients. And then depending on like whether the number of rows is even or odd, you get positive sign or negative sign. And you just take it modulus 3. This trick is used purely because like we have negative sign here, so this sum may be actually negative. It's between -2 and +2, so you want to add +3 and mod 3. Yeah, and now we take a look at the binom function. As you can see from here, it uses some, it works with digits of n and k modulus 3, like base 3, I should say. So like each number can be represented not only in binary or decimal system, but also in base 3 system or base any prime, basically. Basically any base, but we'll talk about prime bases only. So if you want to compute binomial coefficients modulus some prime, then you get that this binomial coefficient is the product of their digits in the corresponding base. The product of binomial coefficients from their digits in the corresponding base. This is called Lucas theorem, I believe, and there will be a link to it down in the description box in case you want to check it out. So yeah, obviously it works in logarithmic time, so that's why I did not really want to spoil the complexity. But yeah, overall complexity is of n log n because this binom function works in logarithmic time. Something like this. I guess there are other ways to compute all binomial coefficients in certain row. You will just take, you will have to take care of exponent of your prime in factorial separate from everything else. But unfortunately, like to find the exponents, you will need a logarithmic time nevertheless. Maybe it gets amortized. Maybe it actually does get amortized, and then you have just normalish linear time row. Okay, so like there are certainly other ways of computing the row of binomial coefficients modulus something. However, I think this is one of the nicer ones. And if you want to learn the proof of the Lucas theorem, then you definitely want to check out the Wikipedia article down below. But that was very nice. It reminded me a lot of math problems that I used to solve in high school. But that was kind of it. And then I went to look at another problem, which I found very difficult because I did not think properly. I forgot one basic idea, and it was what was necessary to solve the problem. This problem is like you want to count the sequences A of length n. They are all elements are non-negative. You know the sum, and you also know the XOR sum of these numbers is equal to 0. And of course, we want to count the number modulo something. It doesn't really matter. It is just standard to get rid of huge values. And n and m are up to 5,000. So here unfortunately, like I was thinking about a lot of stuff. Basically, like basic idea is like you must certainly you will need some dynamic programming over this thing. Now it looks like your dynamic programming will be quadratic because constraints are up to 5000. Unfortunately, what happens is like your partial solution appears to have way too many parameters. Like you want to know the length of the prefix, you want to know the current sum and the current XOR sum. That's already 3 parameters, each of which can be up to 5000. But keep in mind that this is only like the space complexity. The time complexity is one more multiplier of 5000 bigger because you have 5000 transitions per each state. Like you can add any value between 0 and m basically, or between m and current sum, but that's like kind of the same asymptotically. So I realized like this is not gonna work, and it was kind of very hard to get rid of the parameters because I don't know nothing in advance. Like it's not like you can stop 2 positions from the end or 1 position and then there's like, okay, you know the sum of all elements and you know sum of prefix of like all elements but 1, so you derive the last element. Of course, it does not have to match with XOR. And what I basically discard is like there is no way to tell if the current sequence is good or not, can be continued in a good way or can't be. Or at least I did not find such a way. So what I started to think about, okay, like maybe in such problems like XOR related problems, surely you want to do something with bits. What I realized is like these numbers together, they should have an even number of bits set in each position. For the XOR sum to be 0, there should be like 2 bits set here, 2 bits set here, 2 bits set here. Or potentially there should be like, not necessarily 2, right? It can be any even number. Any even number of bits. So in particular that answers are like second test case because m is odd here, so for odd values of m the answer is 0. Because there is no way you can partition an odd number into several numbers with even sum. So yeah. That kind of did not help much. Because here I started to think like, okay, well that is AIs, right? But what I have is m. So I have, I have m equal to 6, right? And I have 1, 1, 0. I started to think, okay, like I can't live with that one. I have to carry it here, right? Because there is no way I can sort this out. And I realized, okay, I can't live with here. I need to take one out of here and into here. So after some manipulations, I got this. But then I realized like, I don't know what, that is not the only possible option. Because then I can take 2 more of this and put them here, which will result in something like this. And it's also a valid assignment if n is at least 4. So yeah, somewhere around here I got stuck because I was thinking in the wrong direction. So I was thinking like, okay, we go from the... So I was thinking from left to right. And as you may probably guess from the break in the video, the recording has died around here. So I'll try to like merge them together somewhat. I hope I restored all the drawings more or less accurately. But yeah, don't, in case you see like some differences, that's because the recording has just died. But yeah, let's get back to our problem. So I was thinking from left to right. So I was going like, okay, we have a conflict here, so let's resolve it and move on. And turn out that's wrong because of this exact issue. Like, you cannot predict what will happen where, which bit will get transferred where. That's kind of like beyond possible. And I'm gonna be honest with you, I had to click on the editorial for this problem. And the very second, like, I just needed to read 2 words from it, and I realized how stupid I was. And the words were like lowest bit. Lowest bit. So I was thinking about like the most significant bit, whereas I should have been thinking about the least significant bit. And indeed, like if we go from right to left, then we can just fix, like we will take that many numbers that have the least significant bit set on. When we see like 4, it means, okay, we'll have 4 numbers, and it means that we subtract from 4 from m, right? That's like literally all I had to read to immediately understand how to solve this problem. And that's just very sad, because it means that I did not I just forgot that you can also start going from right to left. So it's something that should have been on my mental checklist, like of things to try in such a problem. So yeah, now it is definitely back onto this checklist, so hopefully I won't miss something as simple as this again. But unfortunately, sometimes such things happen. That's why we practice beyond like contests, because you need to refresh your mental checklist of ideas that can help you in various problems. And it's another reason why I wanted to share this problem with you, because yeah, like I missed that completely. Hopefully you won't miss it. But yeah, that is something worth noting, that sometimes you need to go from right to left. So what happens is we consider the least significant bit. It should end up with even sum. So we should choose a subset of n numbers of even size. And then we say like, okay, you guys get this bit set on, and all the other guys have it set off, turned off, right? And we know that if we take 0, then the sum remains m. If we take 2, the sum gets m minus 2 or m minus 4, etc. And because we discarded the less significant bit, we should also divide by 2. Because it means like we are no longer considering what happens in the lowest bit, so now every bit that we consider is worth twice as much, which is equivalent to considering same problem for m over 2, or m minus 2 over 2, etc. Next we consider this bit, we say like, oh okay, so you get 2 more. So what happens is from this number, which we got in the previous iteration, we subtract 2 more and divide by 2. And if you can hear something in the background, that's because my neighbors are terrible people. So yeah, unfortunately you may hear some noise. That is just... I've picked a terrible day for recording, I must say. I'll just pause it for now because that's like ridiculous. Alright, let's hope that they paused for a while. We can actually finish this problem already, because it's getting a little bit too long. So yeah, once I realized this, the implementation was kind of straightforward. So I believe this is a right time to show it. And I also used a little bit of Tricolor library for it, just for modular arithmetic. So what happens when we will need binomial coefficients, of course, to like tell how many ways to choose several positions out of n numbers to set the corresponding bits on. But this is something we can pre-compute. So just pre-compute all binomial coefficients up to 5000 times 5000. And then we have our dynamic programming, and dynamic programming works in a very simple way. it's quadratic. It goes over all even numbers, because we already figured out that for odd numbers the answer is 0. It goes over all possible values of how many numbers have the lowest bit set on. Then you subtract divide by 2. This is how many ways you have to solve your sub-problem, which may be potentially 0 if that number is odd. Then you multiply by binomial coefficient, and that is just it. So yeah, it's a shame that I did not solve this problem fully myself, because I just forgot that you can go from the lowest bit to the most significant bit. It's something I definitely should remember, and potentially that's something that you should remember in case you forgot about it as well. So yeah, that's what I wanted to share with you today. I hope you learned something new, for example, Lucas theorem, or just reminded yourself that you can do certain bit operations like in the correct order from the less significant bit to the most significant bit, or vice versa, like depending on what is easier, but you should definitely keep both options in mind as like a mental checklist of what can potentially help in such problems. So yeah, that's it from me for today. Thanks for watching, and I'll see you again tomorrow. Bye bye, guys.